Hello and welcome to our video about electric current. In this video we're going to look at what current is, how to calculate it, what conventional current is, drift velocity, and sources and types of current. So what is current? Electric current exists when there is a net movement of electric charge through a medium. And being able to control this movement of electric charge has enabled us as society to enjoy all kinds of things like lights, radio, television, refrigerators. Current also ignites the gasoline in our automobile engines. Current travels through our electronic devices and allows us to enjoy the use of computers and iPhones. Electric currents are even part of the human body. We can define current mathematically as the rate that these charges move through a section of wire. Electric current is represented by a capital I, and the SI unit is the ampere, and it's abbreviated with a capital A. Electric current equals the charge passing through a given area divided by the time interval. And because our SI unit is in amperes, an ampere is a coulomb per second. Now let's do a little sample problem together. Let's say we have current in a light bulb of 0.835 amperes. How long does it take for a total charge of 1.67 coulombs to pass a point in the wire? I'm going to write down what I know, my current, and also my charge, and I want to find the change in time. I can use my equation for electric current. I can plug values in and solve for delta T. And I get a delta T of 2.00 seconds. So the flow of current in a wire is actually the flow of electrons from negative to the positive terminal. We have something, though, called conventional current. And conventional current is a convention that was established before electrons were discovered. And so it's a little bit counterintuitive. But conventional current defines the direction of flow of positively charged particles. And so the direction is opposite, actually, to the electron flow. This diagram kind of represents this idea. If we have our electrons here, the electrons are actually moving this way, but the direction of the electric current, based on our conventional current definition, is the opposite direction. Charge carriers are a term applied to positive or negative charges that are in motion, either one. Conventional current can be in the opposite direction of charge movement if the charge carriers are negative, but charge carriers could be either negative or positive charges in motion. So when we think about how electrons actually move, let's think about some solid conductor right here in which the charge carriers are free electrons. When this conductor is in electrostatic equilibrium, the electrons are going to move randomly, kind of similar to how gas molecules move. When a potential difference is applied right here across the conductor, an electric field is set up. Here we have our electric field inside the conductor. The force due to that field sets the electrons in motion, thereby creating a current. So these electrons, however, are not going to move in straight lines along the conductor in a direction opposite the electric field. Instead, they're going to undergo repeated collisions with the vibrating metal atoms of the conductor. And if these collisions were charted, the result would be this funny zigzag pattern. But the energy transferred from the electrons to the metal atoms during the collisions is going to be increasing the vibrational energy of all these atoms, and the conductor's temperature will go up. So it would get warmer. The average energy that is gained by the electrons as they are being accelerated by the electric field is going to be greater than the average loss of the energy due to their collisions. So even though we have all these collisions going on inside, of the conductor, the individual electrons slowly do move along the conductor in a direction that is opposite to the electric field. The term that we use to describe the net velocity of a charge carrier moving in an electric field is called drift velocity. In this case, we're talking about electrons as being the charge carriers, and so they're moving in the opposite direction of the electric field. These drift speeds are incredibly small. An example, if we have a copper wire that has a current of about 10 amperes, the drift speed of the electrons would be 2.5 times 10 to the negative 4th meters per second. So those electrons are going to take about 68 minutes to travel 1 meter. That's how small those drift speeds are. Let's just look quickly at different sources of current. Batteries, you all know, are a device that converts chemical energy into electrical potential energy. Generators, on the other hand, are taking mechanical energy and converting that into electrical energy. So those are some different sources of current. And different types of current, you all know, direct current or DC versus alternating current or AC. In a direct current, we have fixed potential difference. Batteries always generate a direct current. It's just an example of a battery from your car. Alternating current, on the other hand, we see that in our homes and in the outlets. The terminals of the source of the potential difference are constantly changing sign. Therefore, we're calling them alternating current. So, in other words, there's no net motion of the charge carriers in alternating current because they're constantly changing, vibrating back and forth. If that vibration were slow enough, you would notice that your light's flickering or other appliances sort of flickering. And so that we don't notice it, alternating current is made to change direction extremely rapidly. In the U.S., alternating current oscillates 60 times per second. So we call that a frequency of 60 hertz. And while batteries always generate a direct current, generators can produce either direct or alternating current, depending on how they are designed. Advanced ideas? Try the conceptual challenge on page 697 of your textbook. Or for whom was the SI unit for current named and why? Or maybe you have another question or something interesting that you'd like to look up. I look forward to seeing what you come up with, and we'll see you in class.